Okay, so now we will move on to the last chapter, which is on electromagnetic induction. We'll be covering the first part, 22.1, which is on electromagnetic induction. At the end of this section, you should be able to deduce from experiment that an EMF can be induced by a changing magnetic field, which you have seen in the previous video. And we also need to state the direction of the induced EMF as one that opposes the changes that produces it under the Lenz law, and also list down the factors that alters the magnitude of the induced EMF. Okay, in 1831, Faraday made the following observation when he carried out the experiment, which you have just watched in the video previously. Okay, he realized that when a magnet was inserted into a solenoid, okay, the galvanometer will deflect in one direction. Okay, the galvanometer is a sensitive ammeter where the zero is in the center. So whenever there is a current, okay, the needle will deflect either to the left and right. And when the needle deflects to the left, it means that the current is flowing in one direction. And when the needle deflects to the other direction, to the right, it means that the current is flowing in another direction. Okay, and when the magnet was withdrawn from the solenoid, the galvanometer needle again deflect but in the opposite direction. Okay, but when the magnet was stationary in the solenoid, the galvanometer needle does not show any deflection at all. Okay, so he also noticed that the magnitude of the induced EMF could be increased by either increasing the number of turns in the solenoid by using a stronger magnet by changing the strength of the magnet, or the speed at which the magnet moves with respect to the solenoid. What do I mean by this? It simply means that either I move the magnet into or out of the solenoid, or I can move the solenoid into and out of the magnet. Is a movement relative to each other. Okay, so explanation. So number one, when I push the magnet in, okay, as the magnet moves towards the solenoid, the magnetic field of the magnet will cut the coil. So there's a continuous cutting of the magnetic field lines of the magnet with the coil. Okay, we say that, okay, the magnetic line of forces, or in short, we always call it magnetic flux, linking the coil have changed. So we say magnetic flux linking the coil have changed. Okay, when this happens, whenever there's a change in magnetic flux linking the coil, there will be a momentarily deflection. Okay, the galvanometer shows that there's a current flowing inside and it's a momentarily one. You see that the deflection goes and come back again. Okay, so it's a temporary one, and we say that an EMF is induced and therefore current flows. But when the magnet is stationary inside the solenoid, okay, there is no deflection at all, because although there is still magnetic field lines of the magnet is still cutting the coil, there's no continuous cutting or no continuous intersection. So we say that there is no change in the magnetic flux linking the coil. And when there is no change, no EMF is induced, no current, and therefore there is no deflection. Okay, and lastly, when the speed of the magnet is increased, the rate of change of the magnetic flux increases, and therefore the deflection also increases. When we move faster, okay, the continuous intersection of the magnetic field lines with the coil also increases, and because this rate of change of magnetic flux increase, the deflection will be more, which means that the induced EMF increase and the induced current also increases. Okay, and therefore this process of getting induced EMF and induced current from moving magnets is called electromagnetic induction. So we have the first law. Faraday's law of electromagnetic induction states that the magnitude of the induced EMF in a circuit is directly proportional to the rate of change of magnetic flux in the circuit. Okay, so there must be a change in the magnetic flux in the circuit to give you this induced EMF and therefore this induced current. And the magnitude depends on the rate of change. Okay, and next, okay, the next part we are going on is the direction of the induced current, and that is given by Lenz law. Lenz law says that the direction of the induced EMF and hence the induced current in a closed circuit is always such that its magnetic effect opposes the motion or changes that produces it. So what do I mean by that? Okay, so we can take a look at this picture. Okay, I know that as I push my magnet into the solenoid by Faraday's law, okay, there is a change in magnetic flux linking the coil, and therefore there will be an induced EMF and an induced current. Okay, but I do not know how does this induced current flow? Which direction does it flows in? And so we need to use Lenz law. Lenz law says that uh, the uh, the direction of the induced current will produce a magnetic field that opposes the change that produces it. So the change that produces it is this south pole moving in. So as the south pole move in, okay, the south pole move in, okay, I want to oppose this south poles moving in. I want to oppose this change of the south pole moving in. So I will induce a south pole on the right hand side of the solenoid. So this side of the solenoid will be induced with a south pole, and so if I were to use the right hand grip rule, okay, so if you were to use the right hand grip rule, I want a south pole on the right hand side over here, okay, then you will realize that at the front of the solenoid the current will be flowing up. Okay, this is by using the right hand grip rule. Okay, so when the current is flowing up, okay, you can trace the current flow like this and then go down, and so the current will be flowing from B to A. And as the current flows from B to A, it will push this this galvanometer or centered zero galvanometer to the left. Okay, because current is flowing from B to A, so the galvanometer will deflect to the left. Okay, so another way, okay, another thing. So just now I'm pushing the south pole in. What happens if now I am pulling the south pole out? Okay, I'm pulling the magnet away from the solenoid in this direction. So now again, there's a change in magnetic flux linking the coil. There'll be an induced EMF and therefore an induced current. Okay, this induced current will flow such that it will oppose the change. So now I do not want this change, which is the south pole moving away from my solenoid. So I will induce a north pole over here because I want to oppose the south pole moving away. So a north pole over here, and by using the right hand grip rule, okay, by using the right hand grip rule, okay, I will have my current all flowing downwards in the solenoid. Okay, and if I trace my current flow, okay, now my current will be flowing from A to B and then go into the solenoid. Okay, so it's going from A to B, and when it goes from A to B, it will push the galvanometer to the right, so the galvanometer will deflect to the right. Okay, so next question. So now what happens if I were to push this solenoid into the magnet, towards the magnet? So what will happen? Okay, I want to oppose the change. I don't want to be going near to this north pole. So what happens by Lenz law? Okay, the direction of the induced current will be such that I will create a north pole on the right hand side of the solenoid because I don't want to go near the north pole. I want to oppose this change. So if I have a north pole here based on the right hand grip rule, okay, all my current should be going downwards, 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 downwards. Okay, so my current will be flowing from this way through the galvanometer and then go down and then go down, go down, go down, go down, and go down here. Okay, so the galvanometer will show a deflection to the left. Okay, so a magnet is held stationary while a solenoid is moved towards the magnet. Okay, so obviously there will be an induced current because there's a change in magnetic flux linking the coil. Okay, and if so, let me hide this. If so, what is the direction of the induced current? The direction of the induced current will be such that it produces a north pole on the right hand side, and so the induced current will be flowing this way. Okay, okay, next one. Okay, work example. Okay, describe and explain what happens to the galvanometer reading when the switch S is first closed. Okay, second part, left close for a few seconds. And part C, after I left close for a few seconds, I open it again. Okay, you may stop the video at this point and pause to think about it. Okay, I'll be going through the answers next. Okay, so my solution, okay, for the first part, what happens when I first close the switch? Okay, what happens to this galvanometer? Okay, the answer is as follows. When I first close the switch, okay, what you will see is that the galvanometer needle will deflect, okay, to one side. What happens is when the switch is closed, okay, the magnetic field, the current will start to flow into the solenoid A, okay, the first solenoid, and the magnetic field lines will increase, or the magnetic field strength will increase from 0 to maximum, because the current, when you close the switch, the current suddenly increase. So the magnetic field of the first solenoid will increase from 0 to maximum. And when it increases from 0 to maximum, there's a changing magnetic flux. And this changing magnetic flux will be linked to the coil of the solenoid B, the second solenoid. And this will result in induced EMF and therefore an induced current. And therefore the galvanometer will show a deflection. Okay, let's go to part B. So I repeat again, part A, when I close, okay, my current increases from 0 to maximum, and therefore the magnetic field also increases from 0 to maximum in A, and therefore there's a change in magnetic flux that is linked to the solenoid of B, and therefore there's an induced EMF in solenoid B, and there's an induced current, and the galvanometer will deflect, shows a momentarily deflection. Next, when the switch S is left closed for a few seconds. So first close already, then you leave it closed for a few seconds. Okay, what is going to happen next is the galvanometer needle will return to the 0 position. Okay, that means there is no induced EMF and no current. Okay, why is that so? Because when the switch remains closed for a few seconds, there is no change in magnetic flux linking the coil. The magnetic field lines linking the coil of B are no longer changing. The current has already stabilized inside coil A, so there is no change in magnetic flux linkage. So the induced EMF becomes 0 and the induced current also becomes 0. Galvanometer needle shows no deflection. Okay, and then part C now. Part C says that when I open the switch again before being opened again. So when I open the switch, okay, what is going to happen is, okay, the galvanometer needle will now again show deflection, but it will be in the opposite direction. So when the switch S is now open, the magnetic field of the solenoid A becomes weaker, so it decreases from a maximum to 0. Okay, so when I open the switch, the current decreases from maximum to 0. The magnetic field also decreases from maximum to 0, and therefore there is a change in magnetic flux linking to solenoid B, and this results in an induced EMF, but now it will be induced in the opposite direction, because just now the magnetic field increases from 0 to maximum, but now the magnetic field decreases from maximum to 0. So the induced EMF will be, and the induced current will be in the opposite direction. So the galvanometer will deflect in the opposite direction. Okay, let's stop for now.